second part of the workshop. As Jason mentioned, this is more about practical usage of OpenFAST. So we're going to get some hands-on examples. As you can imagine, it's a bit of a challenge because this is a diverse group, right? So there's experts, but there's also beginners that have never used OpenFAST. So we'll try to give challenges for everyone here. Yeah, the idea is hopefully all of you has downloaded the folder that Jason sent, where there was a simulation.zip file or a package.zip file, and there were two executables next to it. If you haven't, please go for it and do it. The link is in Jason's email. And yeah, at least like 3 levels of in the audience. We have beginners, standard users, and maybe advanced users. And the idea is like each of you can get something and level up. So because we have beginners and advanced users, I'm going to give maybe, if some of you are bored, I'm going to give some stuff to do, some kind of exercise, some challenges if you don't want to listen to the beginner thing. So that's, you can choose a bit your own adventure. Each time you're bored, you can go back to the slides about hey, how to become better. And for the other ones, there's no shame, and we're very happy to have new users. So we're gonna try to do some simulations together. If you haven't installed OpenFAST, we have people to help you, and hopefully we'll manage to make it work. This is a challenge also because of different platforms and everything. After that, this is maybe more for everyone. What happens if you're on your own and you need to find help about OpenFAST? So we'll talk about this. Tooling is very important, how to pre-process, post-process. So we will also spend a bit of time on this. My favorite tool is Py.View. That's the one I'm using every day 100 times. So I'll probably do a small demo. At the low level, you have the Python toolbox that lets you do some pre-processing and post-processing in Python. And at the high level, you have WISE that we discussed also a tiny bit this morning. Then also probably something for everyone is simulations are a bit more challenging. So OLAF, our free vortex code, linearization and Campbell diagrams can be pretty challenging to do. So we'll try to cover this towards the end. And time for questions, hopefully. And so we have about 2 hours, I think, until the next break. So that's the time we're going to try to spend to work on that. After that, we'll decide, Jason and I, what to do. Jason has plenty to say more about the new features of OpenFAST. Some overview about the tools. Well, in OpenFAST, we have what we call glue codes. You probably have seen this. Glue codes usually combine several modules together. So OpenFAST we actually have FastFarm. That's probably the biggest glue code that we have. But FastFarm can have several instances of OpenFAST within it. OpenFAST is the second biggest glue code that we have that calls all the different modules. And then we have simple driver executables. Those are like calling only one module usually. So the most useful one is probably the Aerodyne driver for me. You have the Hydrodyne driver that is pretty useful as well. Subdyne driver could be useful. And then at this lower level, you have libraries that you can connect and talk to. So as Jason mentioned, if you're using MATLAB, we have a Simulink interface. If you want to plug in your controller and control OpenFAST from MATLAB, we have C++ interfaces, C interfaces for OpenFAST, but also for different libraries. So that's useful if you want to wrap. Even from Python, you can call Aerodyne. We have a C interface for Aerodyne, for instance. And yeah, OpenFAST, the way we work, it's a command line tool that reads input file and dumps output files, right? If you're using the libraries, there's a bit more shared memory going on, so you can actually manipulate the memory. But usually we go through input and output files. Rosco is our open source controller. We are not going to have examples with Rosco because it takes an extra step of compilation. Please get to us if you have questions. The advantage of Rosco is like you compile it once and then you're not supposed to change it ever again. You just change the input file of Rosco to change your controller. And then we have a Python toolbox that is a set of small Python script to help you pre-process, post-process. We have the MATLAB toolbox that is slightly not as advanced as the Python toolbox because it's difficult to maintain both. And we are moving towards Python internally a bit more. And as I mentioned, WISE, which is really for for handling a lot of simulations at the same time and doing DLC calculations and things like this, and optimization. We use ParaView for visualization. One of the extension of the output file is VTK, VTP files. You can load them in ParaView and see them in 3D. If you haven't installed ParaView, we're going to cover it today, so you could try to install it. You could try to install the Python toolbox, but we won't fully cover it today. And that's it. The other ones I can't cover today. And PyDatView, you can also try. If you have Windows, it's very easy to install. It's not too difficult if you have other platform neither. You'll see me using it. If you're curious, you can try to install it. So this is more for the going from standard user to a super user. Look at that. A couple of challenges. Yeah, that's what I mentioned before. So those slides, I'm going to go very quickly over them. And like I said, when we deal with the hands-on practical thing in your board, go back and try to address those challenges. This one is about Luigi. I chose Mario as the theme. Luigi going through the flagpole, and you can study the torsion of the flagpole using OpenFAST. And I've set up in one of the simulation package, there's a folder, I think it's folder number 13, 13 debugging challenge. You can try to run OpenFAST if you're an advanced user. It should take you maybe 5, 6, 7 minutes to solve it. It's gonna crash. There's gonna be error messages. So the best way to play this game is like try to debug. You try OpenFAST on the main FST file until you manage to make it run. And once it's running, trying to make it physical. And this is very representative of what we do in our daily life. Like people send us models and it doesn't run, you know, and we need to figure out what happens. And you're going to experience this as well if you use OpenFAST. Either a colleague sends you a model or you create a model that fails catastrophically. So this one should help you with that. I won't go, but the idea is like you should help your friend Luigi to solve this hacking problem. And this is how it should look like. It's a constant. I put in bold the things that are pretty important. It's about doing an eigenvalue analysis to figure out the frequency of the yaw, and trying to also estimate the aerodynamic damping. And when the rotor is spinning at a constant speed without dynamic stall, this is important. And figuring out what's the frequencies when you have aerodynamics and without aerodynamics. Then I have plenty of challenges that are, that are very geeky. And the problem is OpenFAST is a command line interface tool, so it's quite steep for people who have never used command line interfaces. There's a lot of text files, so I think if you really want to enjoy more the whole using OpenFAST, you need to be better with your text editor, with your environment, with your operating system. So those challenges relate to that. I think it's very useful to have syntax and highlighting. If you only have black and white, it's really hard to read. So set up syntax highlighting for OpenFAST in your text editor. You have features to, most text editors can edit files like 3 different lines at a time, right? So if you don't know how to do this, figure this out. It's pretty useful. For instance, you want to change the file name of the blade. You have those 3 blades, and you know you just want to put underscore new to the 3 of them. You could do this at once. I could demo all of this if you want to. Another thing that is useful is like you put your cursor on one of those file names in the input file, and then you open that file, right? Instead of having to go back to your navigation whatever tool and then open that file manually. It's a very good way to see if your files exist. Also, you just open the main file of OpenFAST, and then you look at those files, and then you open the file that they relate to. You can also open once you have, maybe I think, yeah, last time I did the demo myself to make it a bit more clear. Just you take a file, any of them. Hope that's readable. And yeah, like I mentioned, those things, you want to change this to 0. You could do that. My notepad was off, but that's the example. Opening blade file, where if I want to open the Aerodyne blade file, I go on this, I do something, and I open the blade file, just to make you think why it's useful and how you could use those features. Going back to this, opening a terminal, yeah. If you are in your text editor, you need to open a terminal in that folder, the same folder where you have your file. You can do this quickly. That's going to make your life way easier when working with OpenFAST. Auto completion of path is very useful as well. Like I forgot what's the name of this file. I have auto completion of the files that exist. It's very useful. When you have all those file names, at some point, OpenFAST is going to tell you this file doesn't exist. So having this feature is really, really useful. Back to it. What else? Operating system now. Yeah, if you're on your whatever file manager, can you open a terminal exactly in that folder? There's different ways to do it. But with a keyboard shortcut is easier. You can also go here in Windows, but it takes more time. File comparison, super useful. I don't have folder comparisons. You select two folders, you compare them. Again, if you have a keyboard shortcut, it's better. If you have to click to compare folders, not good. But here I'm comparing two different folders and I can compare the two files. It's super useful when you use OpenFAST in general. But once again, being quick with this, having tools and keyboard shortcut is going to help you a lot. This is not as important. In this tutorial, we're going to have this OpenFAST executable and we're going to put it in different folders. I think that's the easiest way. You could also add it to your system path. If you don't know how to do it, you can figure this out. You can put alias in the command prompt as well. You don't have to. I think in that one, I just say OpenFAST 35 and I have OpenFAST. That's just an alias. More challenges. Now on the OpenFAST features, a bit more physical. 3D visualization, if you've never done this, you can try to learn how to do this with PowerView. So install PowerView and look at this option, write BTK. Make this bigger. If you've never used Olaf, Olaf has features to output vorticity fields. You can open them in PowerView. You can try to do this. It's pretty fun to look at the velocity and vorticity with Olaf. If you don't know how to look at, there's a new feature of OpenFAST where you can output channels all over the blade. So for instance, the actual induction at every different nodes along the blade. If you have never tried this option, try it out. There's some hints here. And plotting them also, we're going to go through that. You can visualize mode shape with the subdyne. If you've never done this, there's some hints. And linearization, we're going to cover it. Again, if you have time, try to install the Python toolbox and PyDatView. So you have everything in the slides. I'm going through really quickly. And if you've never compiled, there's some compilation challenges here for you. That's it. So going back to the basics, those are for the ones that already know OpenFAST and just want to try to get better at it. For the other ones, here's how it works. Like as I mentioned, OpenFAST uses a bunch of input files. It could be very overwhelming at first, but we're going to walk you through some of the examples and get familiar with the main input files. Typically, we like to use the extension .fst for the main file of OpenFAST. And this FST file references other files. That's kind of what I was demoing before. One of the most important one is Elastodyne. We like to use the DAT extension for the modules, for the input files of the modules. And even Elastodyne is going to refer to other files, like the tower file, the blade file. The main FST file is going to reference Aerodyne.dat, which is the input file for the module Aerodyne, which also reference other files. So you can get really easily lost in the chain of files and you can easily have wrong file names. Other tools have everything in one file, but we chose this approach. And so far, this is what we have. So you take this main FST file, you give it to the OpenFAST executable in the command line, and OpenFAST will generate some output files. Typically, our output files have the extension .out or .outb for binary files. And those output files contain time series of your output. So you can think like, what's my rotor speed as function of time? That's the example I have here. So you have the first column will be your time. Your second column will be your rotor speed as function of time. And there's other output files that you're going to see in your folder, depending on the options you activate. There's a summary file, which usually each module can give you a summary file that tells you some of the main parameters of the module, some derived quantities. For instance, subdyne is going to tell you the mass of the substructure. Elastodyne is going to tell you this is the rotor mass, this is the rotor inertia. So you can compare, that's a good way to, when you set up a model, to do quality checks on your models. Echo is, if I turn it off all the time, but it's useful if your OpenFAST is complaining because an input is missing in your input file. So echo is reproducing the input file the way OpenFAST reads it. So you could see if OpenFAST is expecting to read something and in your input file you don't have it, you can compare the two and you can see what's going on. We have .lin file, which is when we're going to do linearization, and .vtk files, which is the visualization files. Those are the main outputs you're going to see for OpenFAST. We're mostly going to deal with the .out files today. In practice, how does it look like? In the simulation folder, if you look at maybe the number 2 case, you'll have those files in your folders that I mentioned: the Aerodyne file, the blade, the polar file, some Elastodyne blade, Elastodyne tower, inflow wind for the wind speed. You have the main.fst, and what I advise right now is to put the executable in that folder and to run OpenFAST, and you should get an output file. I think now could be a good time to try it. Can't remember what I did last time. Well, you don't know how to get OpenFAST yet. Yeah. Forgot what I did last time. I think last time the practical thing was coming next. So let's roll back a tiny bit. Right now, I'm just walking you through what's happening. So in your folder, and I lost everything now. In your folder, this looks like this. You have your main.fst. If you open it up, it's going to look something like this. And again, you have all those different files that reference different files. And you have this output file that is a tabulated data of ASCII data with the time and the different channels that you select. So some notes, yeah. The file names that you have can be absolute. So you can put the whole path or relative to the current file you're in. That's the convention in OpenFAST. So the main file, all the paths are relative to the main file. But once you go into Aerodyne, all the paths that you put in Aerodyne are relative to this Aerodyne file. You could use forward or backward slash. I recommend using the forward slashes. Avoid using spaces. That's a general rule. And if you do have spaces in your folders, in your file names, use quotes around it. Be careful, OpenFAST will overwrite your output files. So if you change parameters in your simulation, and you rerun the same simulation, you're going to lose your output unless you backed it up. So how to get OpenFAST? Again, we provided an executable for Windows. We are aware not everyone uses Windows, but we do have some installation instruction on the documentation of OpenFAST. If you've never checked out documentation, it's on this path, openfast.readthedocs.io, and you'll figure out hopefully some guidelines or some ways to how to install OpenFAST. On Windows, we provide executable for you, so you can click on that link and look at the executable and download it. Again, we've put the executable we're going to use today is in the folder that Jason has sent. If you use Mac or Linux, I think the easiest is to use Conda. Anyone agrees or disagree? Homebrew. Homebrew is super easy. So exactly, try one of the two, whichever is easiest for you. And of course, you can compile from source for the more advanced users. Running OpenFAST, as I mentioned, you do this in a terminal. If you're using Windows, the easiest way to open a terminal is really to go File, open a PowerShell. PowerShell is fine, and then you should be in the folder that you were before, right? And in that case, I don't have any OpenFAST.exe, right? I don't think I do, so it tells me a nasty message. But we'll get to it. We'll put the executable here. So yeah, you navigate to this folder using the command cd if you've never used this, change directory, and then you go from directory to directory, you do cd ... to go one directory back. And at the end of the day, what you do is, if you have the executable here, you do openfast.exe main.fst, and that should run OpenFAST. OpenFAST would tell you some messages, some banner, welcome banner, tells you some information about how it was compiled, the version number. And if it's happy, it's going to be OpenFAST is terminated normally. So you need to read get kind of used to this ugly terminal interface and read what's going on, because sometimes you're going to have some warning or some errors that's going to show up. And we try our best to make those understandable, but it's not always that easy. But yeah, version number is going to be here, pretty important. What's the precision? Single precision, double precision? That's kind of the resolution of your calculations. I use single most of the time, but you could try double as well. OpenMP is useful if you use OLAF or FastFarm. So try to check. OpenMP is the parallelization that allows you to run a bit faster if you have multiple CPUs. So if you find that FastFarm is slow, OLAF is slow, make sure that you compile with OpenMP. So this is where you would know if it has happened or not. Some notes again. Again, you could use absolute or relative path. So you could try, if you know where your OpenFAST executable is, and you can just go and reference it using an absolute path and use your main.fst in the folder that you are. You can also go pick it up relative to your current directory. You can say, hey, I know OpenFAST is 2 directories up, so I'm going to go get it. It's the same for the input files. You can be in the directory where OpenFAST is, and you can go pick up using a relative path where's your main file. And the output file of OpenFAST is always going to be next to your main file. So that's why it's totally fine to do this. And again, you can use an absolute path as well. As I mentioned earlier, I have an alias, so I can. Last time I did this workshop was for OpenFAST 3.2. So if you have done an alias, you can in any folder type OpenFAST, whatever the version that you like, and the input file. That's convenient. Then you don't have to copy your OpenFAST executable everywhere or try to find the path of it. Again, avoid spaces. On Windows, you don't need extensions for executable, but it doesn't matter. Be aware of the direction of your slashes. It's usually good to use the / It works on both Linux, Mac, and Windows. Okay, so now our input files, you're going to have errors because of the input files. So we have some kind of syntax for the input files of OpenFAST, the .fst, the .dat files. We are aware that it's overwhelming. There's thousands of inputs, so which one should you change, right? It is tricky. It just takes time and practice. We don't have a big solution. Hopefully, you're going to use a reference turbine like the NREL 5 megawatt, the IEA 15 megawatt. Those already have all the inputs set up decently, but there are some inputs that you'll always have to change no matter what, like the wind speed. And there are some things that you need to learn with experience. It just takes experience. And throughout this workshop, we're going to see some of the ones that are important. So I'm going to try to highlight the ones that are important when you go from, I don't know, onshore to offshore, for instance. The syntax is always about the same. It's a value, a key, a comment, and then in the comment, we have a bit of a convention that's in between curly brackets and square brackets and parentheses. That's an example for the main.fst. You see the key here is tmax, so total runtime in second, delta t, blah, blah, blah. You also have a key that is called ed file for elastodyn file. You can read the description here. So reading the input file should get you, 50% or 70% there. If you're still confused about what a key or like a given thing does, you can look in the documentation and you'll have more details on how to use it. And the documentation most of the time reference the theory if you're curious about what's the theory behind it. Yeah, that's what I just said. And yeah, again, syntax highlighting. I don't know how people do it without syntax highlighting. I still have colleagues that read OpenFAST files without colors, and I'm like, how do you do it? Just fix it. Output files, yeah. I mentioned earlier, like OpenFAST is going to create a .out file. How do you select what's going to be in this out file, like the rotor speed, the rotor power? I want to know the rotor CP, what's the power coefficient as function of time. Those are specified usually at the end of those input files, and each module has different outputs. Again, how do you figure out which modules has which outputs is a challenge, but I think we'll cover this. But here, this is an example for iodine. At the end of it, do you see my mouse? Mouse? No, you don't. Sorry about that. I'll do it. I've been pointing uselessly all this time. I'm sorry. So iodine, you can select the aerodynamic power, the aerodynamic CP, the power coefficient. So this is, you list them like this as a list of strings in what we call the output list, the out list. For Elastodyne is going to have similar outputs, but they will contain gravity and inertial loads. So like the rotor thrust, the rotor power of Elastodyne is different from the rotor power from iodine, because iodine only knows about aerodynamics and doesn't know about inertial loads and gravity. That's a common misconception when users start using OpenFAST. And as I mentioned, we have this nodal outputs. We'll get through the examples. That gives you, for instance, the lift coefficient at every radial location along your blade. That's for iodine. For Elastodyne, you can have, for instance, the bending moments along the Y direction and Ly at different sections along your blade, tower, things like this. That's what I just said, nodal outputs. And how do you figure out which outputs you can put in every file? And OpenFAST is going to complain if you use the wrong name. That's actually pretty good. But yeah, to really get this, there's a list in an Excel document that has everything. So I could probably click on this. Hopefully it's going to work. Though it's an Excel file, but yeah. So there you go. You have a bunch of tabs at the bottom. Here it's open on iodine, and yeah, good luck with that. 1,500 lines, so that's nice. Plenty of outputs to choose from. You don't see it, huh? That's interesting. What is that about? Share screen. Did I just? I'm gonna share again, I guess. Now you see. Maybe I was in presentation mode or something. So that's, yeah, exactly. So that looks like this Excel file. You have the tab iodine here, and a lot of outputs. So you need to kind of search in it. It takes experience a bit, but they are classified by category. So if you're interested about the hub, you'll find what are the iodine hub loads. The tail fin, we probably won't cover the nacelle, but like the blades has a lot of output, so it is a bit overwhelming. Elastodyne also, you can figure out at the end of it, you have the degrees of freedom, which I personally like a lot, but you're mostly going to be interested in motion of the tower and loads in the tower. So this is where you find those quantities with a description of what they are, in which coordinate system they are, and what are their units. Coordinate systems can also be tricky to figure out. I think I didn't mention that. You'll find those coordinate system in the FAST7 manual. So that's a bit of I should have mentioned that. That's an omission. But yeah, so you can go to the OpenFAST documentation. I think I started writing what was those coordinate system. The best is to find the FAST7 manual. Maybe I'm just going to add this here. Find the FAST7 manual PDF. And at the beginning of it, you have a description of every single coordinate system of OpenFAST. Let me see them. So errors are common. I have a nice little video here to illustrate this. It happens, right? That's common. You're going to bump into many issues. So look at what in the terminal OpenFAST is going to look like this when you have an error. So aborting OpenFAST. OpenFAST is not happy. You have to read a tiny bit up, and then you have some kind of path. That's what we use to, as programmers, to know in which function the error happened. So it was in the function fast initialize old, Elastodyne init, Elastodyne read input, So we kind of guess that the error is about the input file, read primary file, open F input file. Well, the input file elzatodyne was not found. I guess you figure out what the error is. It's a spelling error. You could have other kind of errors like invalid numerical input. More and more, we try to tell you which line the error occurred, but not every module tells you which line of your input file the error occurred. I have written some guidelines about how to troubleshoot OpenFAST. It's not in the official documentation yet, but you can find some information here. Some of the general rules are simplifying your models to the bare minimum. You're going to learn what that means, but that means if you have many degrees of freedom, just use, I don't know, 1, the rotor speed, because you can, make the blade stiff. A stiff model is already easier to handle, right? Imagine your inertias are completely wrong, your stiffness is completely wrong, and your blades are moving too much. OpenFAST is going to crash. So make your model stiff. If it keeps crashing, maybe there's something wrong in the aerodynamics. You can turn off the aerodynamics and then see what's going on. A common mistake is you're using input files that are for version, I don't know, 3 of OpenFAST, and you're using version 3.5. We try now, each time we increase the version number, if there's an increase in version number, you can expect changes of input file. We use 3 digits, so that when the 3rd digit changes, it's fine. If it's the 2nd digit changes, there's going to be change in the input file. And I'm going to go through how you figure out what are those changes and how do you modify your input files again so that you match the version. I think I mentioned this later in the presentation, but we are aware that this is a painful point. Like you have a model that works fine with OpenFAST 3.0, you switch to OpenFAST 4.0 and nothing works anymore. It takes practice. We're aware that it's annoying, but so far we don't have a solution for it. So that's it. Yeah, so that's the part where we could do hands-on simulations. For those of you that have never run OpenFAST, we're going to take like 15 minutes until all of you are able to run OpenFAST. And just before we start, hopefully you have downloaded the shared folder. We're going to go into the simulations folder. And we're using the NREL 5 megawatt turbine, which is a turbine that was designed by Jason here during his PhD. And it's a fictitious turbine. It has never been built. Don't look for it. You won't find it. 5 megawatt is the rated power. 12.1 is the RPM, the rotational speed at rated. The hub height is about 90 meters, and the rotor diameter is 126 meters. So yeah, let's go through case 1. We're almost there, I promise, for the hands-on. In this simple case, we have an onshore turbine. So it's not an offshore turbine, it's fixed at the bottom. And we don't care about aerodynamics, inflow in or inflow, it's just the structure. So we have gravity on. And what we do is, like in this simulation, we set at initial condition a tiny bit of displacement of the tower top. We set 3 meter displacement. So you could expect the tower to just do like this, right? The blades are flexible, I think. So the blades are also not going to be, they're also going to move. So we're going to look at which output channels relate to the blade motion. And we're going to see this happening. We're going to plot those results. So you can navigate to this folder, cd to the folder, and then openfast.exe, the main.fst. And then we have provided 2 scripts, one Python script and one MATLAB script that can open the output file and plot the results for you. Yeah, the important inputs that you'll see in the main.fst is the Tmax. You can play with it if you want. That's the total time of your simulation. The delta T, very important input. Comp elast is telling you, are you going to use elastodyne or beamdyne? We're going to use elastodyne for the blade. So comp elast is 1. And the gravity is important in that case. So, sometimes you do simulation in vacuum. That happens. You want gravity equals 0. But in that case, yeah, it's an important input. In elastodyne, what are important are the TOF. You'll see those degrees of freedom inputs at the very top of it. So that's where you select, hey, do I want my blade to be flexible, my tower to be flexible? And the initial condition, the 3 meter initial condition, is in the elastodyne file because that's related to the tower, and elastodyne deals with the tower. That's about it. I think that's the output that you should get. And I think now we should, hopefully, we have a couple of experts here. We have Mayank, we have Andy, we have Derek, Jason, myself to help you out if you cannot run this. Any maybe questions before we jump or? Derek? Good question. Well, you'll figure it out. It's probably written in the description. I don't even know. Well, you'll see it here. You have 3 meter tower top displacement. So in the plot here, TT, you need to know those. This is how to figure out at first. TT is tower top, DSP is displacement, FA is fore aft. 3 meter fore aft. Hopefully, if you go to this Excel file, it's going to tell you in which coordinate system that is. And that's, I'm guessing it's in the tower coordinate system and it's in the X direction. So this is going to be a downwind. And I told you the response, but like, you could figure it out. That's what I meant. Not you, but like anyone here. Any questions? All right, let's jump in and see who can run this. Yeah.
Not raise your hand. One of us will. No. First. All right, perfect. Yeah, I mean, space is different, but that's okay. Yeah. Do you have some? I can try that. Anyone else? That's very good. I'll tell you. There's a common error, right? Yeah. And then package not I did and then go into that folder.
Excuse me, if I could interrupt. I know you're, deeply, now you've lost it. Sorry, lost your zone. But just 10 seconds. A lot of posters were here at the conference. A lot of them were left behind. They're all at the front desk. If you want to take yours with you, get there by the end of the break at 3:30, after which they will be burned or recycled. Thanks.
So you see this. Yeah. So try to see maybe oh, yes. Questions are ready.
So yeah, let's move on. I know it's painful for the one that have already used it, but hopefully everyone is almost at a stage where they have a plot. I think I messed up the MATLAB script. I'm not sure. If you find out what's wrong with the MATLAB script, let me know. But the Python script should work. So case one, what do we see? We see 4 output channels out of plane deflection, in plane deflection, tower top displacement, displacement side, 4 aft and side. So those are output from Elastodyne. And as we could expect, you know, as the structure is, when the tower is starting to go back and forth, the blade are also moving, mostly in the out of plane direction. You have flapping going on, but a tiny bit in plane as well due to gravity. So that's the first case. If you know, you can move on. It's the same principle now for all of the cases. So I think for the interest of time, I'm just going to go through them real quick. The case number 2 is we're going to turn on aerodynamics. So this time you need aerodyne and inflow wind, right? Yeah, aerodyne is going to compute the loads on the blades, and inflow wind is going to tell OpenFAST what is the wind speed. So if you had turbulent wind, you would also deal with inflow wind and put turbulence in inflow wind. In that case, it's steady wind. So in the inflow wind file, we're going to say the wind speed is 8 meters per second and it's steady. I want to introduce you to the nodal outputs of OpenFAST. So here we're going to look at the actual induction. And so that's something that you set up in the aerodyne input file, where we're going to, at the very bottom of it, you have those nodal outputs, and we're going to say we want actual induction. Some other important inputs. In the main, you need to say comp aero equals 2 to use aerodyne 15. You need to set up the air density correctly. Otherwise, I'm not showing anything again. Yeah. Air density, of course, is a very important input. In your Elastodyne, the rotor speed, you'll find rotor speed is very important. The blade pitch angle, we're going to run without controller, so the pitch is constant, so you better set it to what you want. Here we use 0 because for this operation, for this condition, we don't need any pitch. In the inflow wind file, as I mentioned, the wind type, we're going to set wind type equals 1 for uniform wind, I think, and then the hub height wind speed and the reference height of the wind speed. That's very important if you have shear. In that case, I don't think we have shear. So, but when you have shear, you need to specify what is your power law exponent and the reference height where this wind speed is set. In aerodyne, what's important is the wake mode. That defines if you want to use BAM, dynamic BAM, or OLAF, our vortex code. So here we're probably using DBAM, which is the dynamic inflow BAM, which is the one we recommend anyway when you want to use BAM. You could simplify it. If something crashes, you could use wake mode equals 1, but most of the time you should use wake mode equals 2 because there's more physics in it. AF aero mode is like if you use dynamic stall or not. Tower potent, we set it to 1, I guess, in this case, because we want to have the influence of the tower when it passes the blades. when the blade passes the tower. Yeah. And then some other interesting input is we need a definition of the blade. What is the chord? What is the twist? So those are the aerodynamics definition of the blade. And what are the polar data, like the CL, the CD, the lift and drag coefficients that you're going to use in your blade. So the procedure here is the same. You run OpenFAST on this script, on this main.fst, and the plot script should give something like this. And maybe to illustrate what's important, what you can do, once you figure out how to compare two folders, you can compare those two folders, folder 1 and folder 2, and look at the differences. And that's exactly those important parameters that I was mentioning. Like in Elastodyne, what happened compared to the structure-only case? Well, in that case, we just made the turbine speed at 9 RPM. And before we had an initial condition of 3 meters per second for the tower fore aft. Now we have 0, which is typically probably what you're going to use. What has changed in the main of FST? The main of .FST has comparator equals to 2, which means now we have aerodyne. We have complete inflow equals to 1, so we have inflow in. So you see how it's very important to have a tool to compare input files. It really tells you what has changed between one simulation to the next, and spaces are not that important. So you could ignore the spaces. Yeah. That's just an illustration. I'm going to move forward to the next case. What's important here is now we have aerodynamics in the output file. So at the end of aerodyne, we have set up actual induction to be there as a nodal output. Now I'm going to start using this PyDatView tool that if you don't want to use Python or program each time you want to look at your outputs, that's what I personally use. So let me run the simulation maybe first. Great. What have I done? Did you get this error as well? Or is that just me? That's probably what I did, yeah. What did I do? I said the kinematic velocities, everything. Yeah, just read what OpenFAST is telling you. Okay. Right. So we start again. Now we have this main.out file. I actually set up my environment. If I double click, PyDatView should open with it, and we'll have all of those. Then it's a bit easier to look at all those output channels, right? Like the tower displacement fore aft. What I want to point to in that case is the actual induction. So you have the value for every node, N002, N007. Those are the nodes along the blade. And those are the time series of the actual induction at different locations along the blade. And what I like to use this nodal average tool of PyDatView. So it's OpenFAST nodal average. I usually use the last 2 periods of rotation. It doesn't really matter because we want signals are periodic, so it's good to average over 1 period of revolution, 1 revolution or 2 revolution. And here, PyDatView shows you the actual induction as function of the radius. And what's a bit annoying with OpenFAST when you use BEM is like the actual induction is always 1 at the tip and at the root, so it looks a bit ugly. But this is the distribution of actual induction. We also have the normal force in that output file as function. So that's typical how a blade looks like, right? That's how the force along the blade looks like. Normal and tangential force, that's how they look like. So PyDatView is useful for this. We're going to cover this in one of the examples. I don't think the Python script does this. Python script does show time series, but there are ways to do averaging. Like I mentioned, it's very good to average over 1 period of 1 revolution, because yeah, our signals are typically periodic. This is not converged, so it's not a really good example, but I think if you run longer, you might see that because of the tower shadow in that case, and maybe the tilt, you'll have a periodic signal. Right, so test case 2, steady wind, pretty okay. Test case 3, we start introducing a controller, but because I didn't want to deal with DLLs and everything like this, we're using the basic feature of Servodyne. So Servodyne has a general torque controller, so that's relevant when you're in region 2, when your generator torque is proportional to the velocity to the rotational speed squared. I don't know if I have a plot of it, but so in the Servodyne input file, you can set up this simple general torque control. And I think this is the main input. So I'm going to show the pointer again. It's this variable speed control. You have to set it to some values. In this region 2, K is the proportional constant between the torque and the rotor speed, and some other inputs. So if you compare those two folders again, you'll see what happened. And, well, in that case, yeah. But if you look at Servodyne, those inputs are pretty important. And this time, another thing that we did is we're not doing constant rotational speed, so we have the generated degree of freedom in Elastodyne that is set to true, which means that the rotor speed can vary. And if you don't have a controller, you'll have weird things happening because your rotor speed might overshoot, might overspeed. The controller is here to give an extra torque, on the other hand, to make your rotor speed kind of flatten out in steady wind. So yeah, you could try. I think if you try running that one, you could probably plot. So maybe step 1 is you compare those two folders, 2 and 3. Let's see what happens. Now we have comp servo equals 1, right? So now we're using a controller. So that activating modules happens in that big section of the main.fst. So now we need the Servodyne file. And if you look at the Servodyne file, I have nothing to compare against, but those inputs, vs underscore variable speed underscore, those are the input that are relevant in that case. If you wanted to use Roscoe, what would happen? Let me I don't like that editor. If you were to use Roscoe, you would look at PC mode for the pitch control, and you'll set it to 5. Variable speed control for the generator, you would set it to 5 as well. If you look at the descriptions, 5 is for bladed style DLL. And then you'll scroll down and you'll find this section, bladed interface. And this is where you would specify the Roscoe DLL and then the input file for Roscoe. And then you'll have Roscoe running with your simulation instead of having this variable speed, simple variable speed controller. That doesn't work before region 3 when you pitch. And I have the results here, so I don't need to rerun it. But if I look, we have rotor speed, generator speed, and I have generator torque as an output. And I could probably plot the generator torque as function of generator speed. And you can see it's kind of it's supposed to be. I'm guessing, the simulation is not long enough, but we should have a squared relationship. I did the opposite. I did the opposite of that. What I wanted. Gen speed, gen torque. You should have this kind of squared relationship. Any question on that? Simple. Moving on to the examples. Simple controller. Next step to do is to add turbulence to your simulations. So to use turbulence, you need TurbSim to generate a turbulence file. Turbulence file, the typical one for OpenFAST are .pst files. And yeah, I think I provided in the package turbsim.exe. So you could try this. You could go to this folder. Now we are to simulation 5, sorry. You'll find an input file for the turbsim box. .enp in that case. And this defines how you want to set up your turbulence grid, how many points you want to use, what you can also set up a shear profile in it. There are different turbulence models that you can use. You can see here I use some shear. And I set it to default. So that means it's going to use, let me see what I did here. It's going to use, default is probably 0. I think maybe there's no shear in that file. I think it is. The standard is going to set it. Like that, exactly. The standard are going to set it. So I think maybe that standard is setting everything. Yeah, this is like you need to read all the descriptions to know what's going on. but there is some power law, a default power law that the standard is going to set up. But if you run TurpSim on this input file, you'll get a BTS file, and this BTS file has this turbulent wind in it, and it's a 2D grid with a turbulence as function of time. I cannot display it with PyDat I can only display the velocity at the middle of the box, for instance. But it is a 2D grid. You have for every single point of it would look something like this, right? For every horizontal point and every vertical point, you know the time series of the turbulence. And I don't know if we should go through generating the BTS file. Who is able to generate a BTS file here? Raise your hand. Half. Maybe I can help a couple of people do it. Just what do you think, Jason? Or should we move on? So yeah, if you cannot generate it, the TurpSim is really the same thing. You go in here. We provided the executable. So you have TurpSim.exe. You copy it. You go into your package folder, simulations, turbulent wind. You open a terminal here. You do TurpSim, then the name of the TurpSim input file, and that will generate your BTS file here. And if you can't do it, you have the BTS file in the results folder here. I gave it to you here. So that's it. So now you're able to run OpenFAST. OpenFAST, the inflow wind file of OpenFAST is going to read the turbulence file. If you look into this inflow wind.dat, you can see that now wind type is 3 for turbulence. And this is the name of the input file that we're using. And the output should look at what you have on the slide. Maybe the next slide is going to be a turbulent output. Another thing that we do in this simulation is we added the tower shadow, which I try to kind of explain here, or like the influence of the tower when the blade passes through it. And that's about it. If you compare the two folders, you can see what's going on when you go from steady wind to turbulent wind. And that's probably the best way to learn, is to compare those folders. And that's what I was mentioning. Wind type equals 3. We set up a BTS file, and the aerodynamic file has changed. Before it was AF aero mode equals 1 for steady aerodynamics, and now we're using this dynamic stall model with AF aero mode equals 2. Before tower potential was 0, now it's 1. So now we do have the tower influence. And tower aero means now we have the forces from the wind on the tower, which is important as well. The wind is going to have a small drag on the tower, and the tower is going to deflect as a function of that. Go ahead.
Rotor and the tower, how does it work?
So OpenFAST is going to complain if your TurpSim file is not big enough in the Y and Z direction. So it definitely needs to cover your rotor. That's for sure. So I made sure of this here. This is where you kind of set up the grid in the TurpSim file. Those dimensions here make sure that I cover the entire rotor.
Get it larger.
Usually larger, exactly, because your turbine is going to move a tiny bit, right? And if you want to have this influence of the aerodynamic force on the tower, you need the wind to cover this tower as well. So that's something that can be a bit tricky at first. If you use a BTS file, BTS format, we have this, what we call the lollipop, which is this flag here, right? Aerodyne tower. So your BTS file has actually the time series of your grid that you specify, but it also had the time series from at the middle up to the ground. So this way you don't have this error that's going to show up if you run OpenFAST with a BTS that was generated without this set to true. Aerodyne is going to complain, it's like, I don't know what's the velocity here at that node, because you covered the rotor, but you didn't cover the tower. So the lollipop version, it looks like a lollipop. That works great. If you use a man box, because you can use different kind of file format, you don't have to use this BTS. Your man box better cover the ground as well, like all the way to the ground. If you use TurbSim to generate turbulence boxes for fast farm, then you need the box to cover your entire farm, right? Or yeah, at least if your box covers just the region of the turbine, you need to account for the fact that your turbine might yaw, so a tiny bit bigger than the rotor area. Other questions? Yeah.
It's not related to this, but we speak just to run OpenFAST next week for experts, but we run a lot of cases.
Yeah.
What's a good procedure to like keep an overview of this output files I generated them with these input files? At the moment, I save all my input files, but I'm not sure that's best practice.
My way of doing it is different folders. I do parametric study within a folder, so I have different FST files in one folder I compare the different FST files within that folder, and I keep the output files there. After I'm done with the project, I delete all the output files and I keep the input files. I personally delete output files when it's a long time. You know, you don't want to keep all this data, right? I use a GitHub repository for everything I do. I think this one doesn't have it, but so all my FST and my DAT files are in a GitHub repo, so that if I do a demo and I start changing an input file and I forgot about it, and then my results don't match anymore, at least Git will tell me, hey, you changed that file. That's definitely top on my list of recommendation. Always have GitHub repositories for all of your. You just exclude all. Don't put the output files in the GitHub repo. You ignore them, right? But all the rest should be in a GitHub repo. Your scripts and input files. Good question. Any other questions? I'll move on to the next case, I think. Turbulent wind, it's a bit more fun, right? The turbine is moving a bit more. It's a bit more realistic. If you look at the output file, you'll see those fluctuations going on. And here we still have servodyne, I think. So our rotor speed is having some variation. The generator torque is following it because we have this simple controller. And that's about it. You know, you can look at the slides if you're more interested. Next, it starts to be more challenging, is going offshore. In that case, we're going to use the monopile version, the OC3 monopile that was developed as part of the OC3 projects. And yeah, so again, just like TurbSim, you could do turbulent wave, right, or more advanced wave. In that case, it's only a regular wave that I'm going to use, so simple sinusoidal variation, and Hydrodyne can do this very easily. In the next release of OpenFAST, I had a question about this. We're going to introduce the C-state module, which is a bit like InflowWin. It's a module that gives you time series of wave at different points in space. Hydrodyne does this already, but now we're kind of separating. We keep Hydrodyne just in the future just to compute the forces, and C-state to compute the wave and the current. And so really, what is the C-state? In that case, everything is together. The most important inputs, maybe I'll just do the diff again, like offshore and on periodic steady weight. I'm going to compare 5 and 3. And now we have a Hydrodyne file. You can look at what changed in the main.fst. Well, time step. Sometimes here interporter. Sometimes when you start having subdyne and Hydrodyne, things can get tricky in terms of time steps and things. Things will get better once we go have the tight coupling. I don't think I need interporter equals 2 here. No, sorry. Here I started using a correction step. On my right, I have the Hydrodyne case. But what's important is the compute hydro. So now I have Hydrodyne. I have subdyne, which is going to deal with the monopile itself, because the Elastodyne cannot do the monopile really. So I need those 2 new modules. And in the next version of OpenFAST, you'll have another module, which is the C-state module as well, to say, hey, yes, I want C-state. Water density all of a sudden becomes important. It's pretty obvious. Water depth, pretty important. And yeah, now we need an hydrodyne and subdyne file. Those files are pretty long. I don't think I'll go through them. Takes a bit of learning, but for monopile, it's fairly simple. You just define the few nodes that you have, and hydrodyne can interpolate between those nodes. And so if your monopile doesn't change too much diameter, if it's constant diameter, or if hydrodyne will interpolate maybe every meter, every 5 meters of your input file. Subdyne can also do this. You can define a couple of nodes and it will subdivide the structure for you. Maybe I want to show you how to run. Let's just do a run and see what happened. Because I think one thing I forgot to mention in the previous case is one of them was generating BTK files if you want to visualize it. If you're curious about visualization, which one was it? Case 3 generates VTK files. So if you've never used PowerView, I'm going to run the case 3 for you. OpenFAST 35 main. You're going to see a VTK folder has been created by OpenFAST, and OpenFAST is generating a bunch of VTK files in it. So if you have installed PowerView, if not, I recommend installing it. You're going to be able to visualize the turbine as it moves. So I'm going back to case 3 here. So you open PowerView, you find your folder. I don't know where I am. Work, fast, workshop. It's 3. You see this VTK folder, and PowerView gathers everything by time steps, so it looks a bit cleaner than the full folder. So you could open everything if you wanted to, all at once. You apply, and then you see a turbine, which is a bit more exciting than looking at this time series. You can play, and you can see the turbine. It's a simple simulation with only a few VTK, so it looks very not so smooth. Because I didn't want to generate a bunch of inputs, so here I'm outputting at the very low frequency. But that's it. That's how you could visualize, and now we can visualize the waves. I don't think I do this in that example, but it's the same principle. So to have VTK visualization, it's this in the FST file. You have write VTK, you set it to 2, and then you can visualize. Question? Yeah. Say that again? So I went to the VTK folder. So in PowerView, I said open. Did I close PowerView? I think I did. Yeah, you go open to VTK, and then it shows you, for instance, it's going to show you those files. And I opened all of them, but you can open just the tower, just the blade, depending on what you need. Question? Yeah.
Earlier on, Jason showed a beautiful animation of the key planes with files. Was that also in PowerView?
Yes, to some extent. Yeah. So you could see in this animation, you saw the turbine rotating. That was from the VTK of OpenFAST, generated by FastFarm, kind of. It's the same. And FastFarm also outputs flow fields, and that's what you were seeing. You had the turbine rotating with the flow field at the same time.
OpenFAST does not.
No. Olaf can output the flow field. That's about it. InflowIn has a feature, but it's not really the same. Yeah. But you could use FastFarm with one turbine, and then you'll have the flow field. Good question. Other questions? Going back to case 5, hydrodynamics. I'm going to run it in front of you. I think what's important here is when you deal with subdyne. So I guess subdyne in that case generated a .json file, which contains the modes of subdyne. And it's always a good idea to verify that your modes make sense. Your subdyne mode, your substructure modes make sense. For this, the way it works, as I mentioned, subdyne input file is a bit long. You can't cover it all, but at the end of it, you have some options to say, yes, I want to see what are those CB modes, the Craig-Bentham modes, and the FEM modes. So Subdyne uses a FEM representation, but FEM, finite element method, has thousands or hundreds of degrees of freedom. That's a bit too much. So internally, Subdyne reduces those 100 degrees of freedom to few modes. The Gaussian modes, which are rigid motion of the interface. So usually the tower substructure interface moving rigidly, and then the internal Craig-Bentham modes. And you can visualize them when you set this option to 1. You have this JSON file that has been generated, and then you can go to this 3D anim, which is a GUI generated. You go to this GitHub page, you can, no, that was a mistake. You run it. That's for a jacket, but what we want is take the one we just generated, we drag and drop it, and now we see our monopile moving. So those are the modes. So this is the mode 1. I'm guessing red is X in this is the X direction. So this is like a fore aft mode. This is some kind of good side mode. This will be some gravity mode. And then you'll have the bending. Those are not full FEM modes. Those are Gaussian modes, because if you look at this, the top node mode translates. It's a pure translation. The true FEM mode will have translation and rotation at the same time. You can output the FEM mode as well using the flag just below. You set it to 1, and then you'll have the FEM modes. If you look now, I have 0. I only have, no, sorry, my bad. I have 6 Gaussian modes. You'll always have 6 Gaussian modes. That's just the way it is. It's those 6 degrees of freedom at the top of Subdyne. If you only have 1 interface node, but maybe in the future we'll have more. And then you have those Craig-Bentham modes, which are the internal modes. And the internal modes will always be fixed at your boundaries that you set. So they don't move at the top and at the bottom in that case, because it's a fixed bottom foundation. So that's why the first Craig-Bentham modes is looking like this. Second one is going to be the same in the other direction. Third is likely a torsion mode, so we don't see it in that example. And that's like a second fore aft internal mode. And yeah, there's a couple of things you can do with this GUI too. If you're tired of it moving, you can just say, hey, stop moving, or yeah, show me the max. Anyway, this is probably what I want to say when you go offshore. In theory, you should use a different tower. So I probably did something wrong here. If you remember that if you change the boundary condition at the bottom of your tower, you need to change your tower modes. Right, of Elastodyne. How can you see that? Let's go back to the first case. We had 3 input files for the blade and the tower. This is where I like PyDAView, is that you can throw input files at it. So you can throw the tower, and it will show you the shape functions of the tower, because you specify them in the Elastodyne tower file. You specify polynomial coefficients. It's a bit of a pain to plot it. So to plot it easily, PyDAView does it for you. And then you can see this first fore aft looks like this as function of tower height. The second tower modes usually look like this. And those, I probably took the Elastodyne tower file for the offshore NREL 5 megawatt baseline. There's different tower file that you can use based on which foundation. So in theory, you should figure out those coefficients yourself as soon as you change the design of your substructure. I'm not explaining this today, but we have a tool called B-modes that you can use to find those shape functions. So you change the boundary condition at the bottom or at the top, the inertia. In theory, you need to regenerate a new tower file. So that's what I should have done here. If I compare those two, in theory, the tower file should be different because one was onshore, one was offshore. But my Elastodyne file, I use the same, which is okay. Ah, look at that. Okay, well, you see, well, I did something right. I'm using different tower files. So now let's compare those two tower files and see how different they are. I prepared this 1 year ago, and I think I forgot some of it, so I apologize. But so I'm going to open the offshore and the onshore tower files, and you can see some differences between them. So the mass is a bit different mass, different modes as well. The stiffness is a bit different, fore, aft, and side, and the shape functions end up a tiny. Usually, the first fore, aft is usually the same, but it changes a tiny bit. What could vary a lot is the second modes. The inertia can change a lot. Also, the inertia of the nacelle is going to change a lot your second modes, not so much your first modes. And again, the sides are also a bit different. You can also compare the fore, aft, and the side. They are going to be a tiny bit different again because your inertia is different in different directions, right? That's what affects. That's why those two modes, the fore, aft, and the sides, are different. Even though the tower is tubular, completely axisymmetric, you have different modes, and the same for the side and fore, aft. So again, this is where PyDatView can be useful. You forgot what you did, you can compare your files and figure out what's going on. So yeah, one thing to remember, if you go from onshore to offshore, change your tower file. And I guess since I did it, I probably mentioned it in the slides. So you could go back to the slides and hopefully it's mentioned. Okay, and that's about it for the tutorial, basic tutorial. Then I have some explanation about what you do when you're alone. Talking about the tools, I'll probably go very quickly about this. And then we can look at what happens when you have OLAF and linearization. So I'll probably have to go very fast if we have half an hour.
Well, pause and say, yeah, do people want more help with running some simulations, or should we just do some more maintenance? We have quite a bit of time left, so I'll say.
Yeah, just have a question if I may.
Yeah, questions are good. Yeah.
What is a good practice when you run OpenFAST simulations? Just sanity checks. What is typical stuff you heard?
So yeah, that's why I use PyDatView is for sanity checks. Obviously, you know, when you do a paper, you're not going to use PyDatView for your plots, but sanity checks, input file sanity checks. So yeah, looking at your shape functions, looking at comparing files like this, like just plotting what is the difference between those two files. What did I do? When you look at the output file, start simple. So first look at let's look at the turbulent file. You know, wind speed, is the wind speed the right one? I like to organize my outputs in the output file in an order that kind of the most important ones are at the top. The basic ones are at the top. And then I like to go from blade tip to the tower bottom. I guess I kind of did this here. This is the blade thing. Then you go to the shaft, kind of. Then you have the tower displacement. This is not actually the case. This is the blade root. But anyway, then you have the tower base. So I don't know. I like to organize it like this. So you usually start from the top, which is the blade, making sure your blades act decently. You don't have crazy deflections. Your tower top fore aft is decent. You know, if you have 10 meters displacement fore aft, something is bad. Here, it is a simple simulation, but yeah, visual inspection is the best thing. You know, generator torque, imagine your generator torque is 0. Something is wrong. If your generator torque is 0, so it's good to look at it. It could be that you forgot to turn on the controller, something is bad. Look at your rotor speed, very important. If you expect a constant simulation, like, or if you do your wind speed is more or less constant, you expect your rotor to be not changing too much. The classical error is you forgot to turn on the controller and your rotor speed keeps increasing and then kind of plateaus at, I don't know, a high rotational speed. Sanity checks. Again, start simple, no matter what. So always turn your degrees of freedom off and progressively introduce more degrees of freedom.
Once you're comfortable, if you keep the process, you're going to get more like automated scripts. You won't do that every time, we just script it out. But I think we should ask, I guess, now, so maybe look through some case, we can spend some time with people do that. Or maybe we could jump to the, more advanced simulation, like scale diagrams and a lot of stuff. We just will both on what you prefer to do for the next half hour. Very good. We'd rather spend some time running through the case that the manual showed. Have this come and help you. Option. Raise your hand down. Otherwise, we do the more advanced demos and things. So we'd rather spend some time doing debugging. Simulations. That's there.
Sounds good. And we can help you debug. I'm happy to help. So I'm going to go very quick about section 3 and 4, like super quick. I'm sorry about that. Just you have the slides, so that's why I'm going quickly. If you need help, go to the documentation. This is the link. As I mentioned, input files changes from version to version. So what do you do when you have errors like, oh, your input file, someone had this error actually, because they were using version 3.4 and the inputs are for 3.5. So you'll see errors. Where do you find those changes between input files? It's pretty important. I think you should listen to that. We have this link that you could click on, and it's going to tell you from one version to version what changed. Second thing is what you can do, and that's usually what I do because I'm too lazy to read. I use the rtest directory, I clone it, and I can see this rtest direct repository has input files for every version of OpenFAST. So it has tags on it, so you can clone a given tag. So you clone version 3.5.1, version, I don't know, 3.6, if it ever exists. And then you compare your input files with the input files that are on this repository. So again, having a comparison tool is going to help you. You're going to clearly see, oh, there's a line missing. So those are my recommendations. And it's going to happen to you because we change input files all the time. But that's the procedure. Say that again? Do I create them manually? Or no, I use what I showed you, this comparison of files, exactly what I did when I compare folders, right? That's what I do. I don't have a script. We should have scripts. We used to have MATLAB scripts to do it. For me, it is, I deal with 5 different versions of OpenFAST all the time, and doing comparison is not that hard. So I never got to implementing a script. Input file changes all the time. Now the tools, I'm going to go quickly. I think I gave you already an overview of PyDatView. Hopefully you see why it's useful. Again, I'm a programmer. I don't really like GUIs, but I found PyDatView extremely useful. Some of the quick demo I can do is there's a bunch of tools. You can do FFT. This example is not very good, but you can look at your what are the frequencies in your signal. Super useful. Probability density function in that. This is not a good case, but you could look at that as well. When you have signals that have completely different magnitudes, you could use this min-max feature, so it scales everything between 0 and 1. It's actually more useful than it could sound. Sometimes also if the mean is not the same, there's some tricks you can do here. Other things I use it for quite often was what I was showing for this, the case with the actual induction as function of the span. This I think is really, really useful. That's also a sanity checks. If you don't know what's going on with Aerodyne or Elastodyne, what are my loads as function of radial position? Is this OpenFAST nodal average? And I like to do a couple of periods, average, and then you look at this radial distribution. I think it's really, really useful. Another thing tool that I use very often is the mask. Oftentimes you have transient. This is not a good example because it's steady, but that's the terpsim file. But okay, I can mask the terpsim file. I can say, oof, bad example. All right, fine, fair enough. You could say, I only care about time after 20 seconds or 10 seconds, and you apply a mask. This way you don't have all of those transients that pollute your signals. I use this very often. applying a mask. Another thing you could do is applying a filter, the moving average filter here. Doesn't look that great, but this is what moving average does. And what else do I use very often? Resampling is, I use all those tools all the time. Standardizing the unit is useful. Like, it's awesome. Mask is awesome. Mask is the best one. Okay, good. But I agree. Yeah, it's pretty useful. Standardizing a unit, sometimes some output channels of OpenFAST are in Newton meter, others are in kilonewton meters. It's a bit annoying. So this will take care of this for you. And yeah, you have curve fitting. Look around, there's a couple of useful things here. Back to this. So that's PyDAView, instructions of how to install it. Python toolbox, I recommended some of you to install it. Those contains the low-level Python tools to read a file, plot a file, and change input files. So if you want to script all of this, there's some examples in the Python toolbox to do this. It's fairly easy. And if you look at the simulation package that you got, there's one folder that is about Python examples. And those are those examples, like how to read a fast input file, change the air density, and write another input file. You know, it's 3 lines of code, and reading an output file and plotting a, you know, it's also 3 lines of code. So PyFast is here for that. This Python toolbox is here for doing those simple changes, looking at the blade. Everything that PyDAView does, actually, you can do with PyFast. Maybe that's another feature of PyDAView that I like, that I recently added, is you can export a script. And you can export it using the PyFast library. And then you have the script that does exactly what you did in PyDAView. So it has the filter, the radial averaging. Let's just see if I was plotting this. Let's see, live demos is never a good idea. I would update the script. I can run that script. Let's see if it does, if it works. Yeah, so it works. So you can take this script, you can save it somewhere, and you're ready to like do mass production if you want to deal with 1,000 input files, right? So it really is to speed you up, to get you up to speed. But PyFast, yeah, this is what PyFast does, some low-level things to read and modify files. So those are instructions of how to install and run some of the examples. Then we have WISE and ROS code that we can't really cover in this workshop. But go ahead. Yeah. But we welcome contribution. If you want to submit pull requests and bug fix, you know, like we will include them. That would be great. Other questions? No. So we have WISE, which has plenty of examples that you can check out. This is really if you want to do optimization studies, parametric studies, and more mass production things. Rosco, some people were compiling Rosco already. You need to compile it, but once you have it, you don't need to change it anymore. That's the beauty of it. And it has also some Python examples to get started. So now you switch to the more difficult run. And now we have what, 15 minutes? Yeah, but you have the example files in your folders. What's really, I'm going to just give an overview of what's important. When you use OLAF, just don't use it blindly. I mean, don't use OpenFAST blindly. As you can see, it's very difficult to use. OLAF is probably even more difficult to some extent, maybe. But we have some guidelines. So read the guidelines. We have a Python script within it that tells you what to do. I guess that's, I thought it was going to be obvious, but in the shared folder, I give an example of this Python script. It's params.py. And it tells you how to set up the inputs of OLAF. And the ones to pay attention to is like the number of NAWEA panels, the regularization factors, and that's about it. But why do you need a different? You also need to be careful that if you change the rotational speed, you need to change some inputs of OLAF. If you change the mean wind speed, you need to change some inputs of OLAF. So remember that. It's not just you have one OLAF file and that's good forever. You need to change it each time you change your wind speed and rotational speed. If you change your rotor size, you might need to change the OLAF input file as well. And all of this is because we have expressed everything as function of number of time steps. And we want the simulation time not to be too long. And we like to have maybe like vorticity shed every 6 degrees of revolution. So if your rotor speed changes, that's why your delta T should probably change for OLAF. So you have an example in the package. You could try to run it, and the first time you run it, you'll have also Python script that does some plots for you, and you'll notice like results are crazy. I didn't zoom in, but this is the power coefficient is 0.8, the thrust coefficient is 1.0. So if you run OLAF and you have crazy values, something is wrong, and most likely you need to retune the parameters by running this Python script. And you can look at the velocity field in ParaView or look at the vortex wake in ParaView. And in that case, the vortex wake is very short. That's it. That's at the end of the simulation. This is how your wake looks like. And the velocity field goes up to 30 meters per second. So something is definitely wrong. So here the regularization factors were too low. So that's why you had crazy velocity. And your wake was way too short, which is why you have not enough induction. If your wake is very short, you basically barely have any induction at your rotor. And then your thrust becomes crazy high. So once you run the script, you rerun the simulation and you can plot, you have a decent velocity between 0 and 16 meters per second. And then you have a wake that is longer and looks decent. And the simulation is not converged in that example, so you need to run way longer. But the scripts tell you when the transients are over. That's what I say here. You need to run longer. Now, linearization, I have a small slide about the theory behind it. It takes time right now to do linearization. Our colleague Derek is streamlining the process. If I were you, I would probably wait 1 year. And then that's about it. Or you can go through the steps I'm going to put you through. But the theory is if you have a system with a dynamic equation of that form, X is your state vector, U is your input, you do a Taylor expansion of this about a given point, which I denote X0, U0. And this is your linear model. For small perturbation of your state, this is how the change in time will be for small perturbation of your state and small perturbation of your inputs. This is a matrix A. I guess there's a B matrix here, but the most important one is the A matrix, because if you extract the eigenvalues of the A matrix, you get the frequency and the damping. And this is where you could already, one of the challenge, the Luigi challenge, I don't know if anyone fixed it, but managed to hack it. But you do eigenvalue analysis of this A matrix with structure and without, without aerodynamics and with aerodynamics, and then you can compare the eigenvalues of this A matrix, and you can see what is the contribution from the aerodynamic damping in particular by comparing the eigenvalues and the eigenfrequencies and the damping from those A matrices. And OpenFAST does this. I think Jason covered some of it. There's flags that you need to set in the input file. I think I'm going to do a comparison of folder to show you which files. One thing to note is since our systems are usually periodic, which we are kind of removing at the moment a bit, but I think the true reason is we have states that are in the rotating frame of reference. And so the blade elastodyne degree of freedom is you have maybe, if you had only one flapping mode, your blades can flap at different times. Basically, that's what's happening. Because you have 3 blades, they could flap all of them at the same time, or it could be the first blade flapping, then the second one, and the third one. And then the opposite, they can flap in opposite direction, maybe the first one, then the third one, and the second one. They can kind of go in both sides. Just for this flapping thing, it could happen in those 3 different ways, collectively or forward or backward. And so because of this, we use this MBC transformation, which is the multi-blade coordinate transformation, that goes from this rotating frame of reference to the ground frame of reference, more or less, or at least it splits this mode, that it's just one single mode, into 3 modes. So it's something to think about. You'll see sometimes we like to use different lin files over the rotation. That's because we know the states are changing and they are periodic, so we like to use different linearization points along the azimuth. In practice, what do you do in the OpenFAST input file? We have a flag at the bottom of it that says linearize. You set it to true. If you do just, you know you're not rotating, you will typically run only one linearization time. So n lin times equal 1. And you set up at what is the time where you want to linearize. So here I'm going to linearize at 500 seconds. And OpenFAST is going to generate a lin file that contains the A matrix I was talking about. Then you will open it in Python, for instance, and do the eigenvalue analysis to get the frequencies and damping. So you linearize, it's quite important. It's usually best to linearize at an equilibrium point because that's where the system makes more sense. And it's your responsibility if you use this basic algorithm to find when is the system, has converged, when it has converged. We have now implemented a trimming algorithm that can help you. It will internally try to force the system to go to a steady state, quasi-steady, periodic steady state, and then linearize automatically. I'll show you how that works with the examples. So for instance, you want to know the blade frequencies. What are my natural frequencies of my blade? You can do it with OpenFAST. You set every degrees of freedom off except for the blade. And that's what this first case is. So if you run case 10, that's exactly what this is. I'll do a small comparison. Blade only, and let's just compare with, I don't know, the steady wind. Hopefully they look similar. So the main difference is, I guess I set gravity to 0 in that case because I didn't want that influence to influence the mode. I'm looking at the mode in vacuum. Most important one is I'm using linearize to true, as I mentioned, and I'm linearizing at t equals 0. Because in that case, I have 0 gravity. There's no reason for the blades to move at t equals 0. Other thing to look for is the elastodyne file. I set every degrees of freedom to false, except for the blade. And then I have no rotational speed and no displacement of any kind. So that's why I know the blade is not going to move at t equals 0. I linearize at t equals 0, and I'm going to get a linearization file. OpenFAST will generate a .lin file, and you can use the Python script that is provided. It's going to open this A matrix, do the eigenvalue analysis for you, and give you natural frequency, damping ratio of the flap, first edge, and second flap, because those are the only degrees of freedom we have for elastodyne. You could do the same thing with beamdyne, but then beamdyne is a FEM, finite element model, so you'll have hundreds of degrees of freedom. But the first few modes are usually the one we care for, and you can see what are the frequencies and damping. I'm not going to run through it. It's really the same. You run OpenFAST through this FST file. You look at the lin file. I have a Python script that can give you those frequencies. Now, it gets more complicated when your turbine rotates. In that case, am I using the trim? I don't think I'm using the trim, but let's again compare. Same principles you're going to set in the FST file. You set linearize to true. And I'm using calc steady. Okay, that's good. So I'm using this trim algorithm that I was talking about, which is what's going to help you to linearize at the rotor speed that you want. Okay, if there's some controls that's going to happen. So if you are in region 2, you want to use the torque trim case. If you're in region 3, you want to use the pitch trim case. What does that mean? Is like when you are in region 2, Servodyne will try to adjust the controller, the generator torque, so that your rotor speed is what you specified in the Elastodyne file. If you're in region 3, Servodyne is going to try to adjust the pitch angle automatically until you reach the rotor speed that you want. So we recommend using CalcSteady. Sometimes it doesn't converge. When you use CalcSteady, it's good to have a large Tmax, which you can see that's what I did here. I set up gravity on. More and more we remove gravity to avoid periodicity, but in that case we have gravity. And I'm setting up that I want 36 lean files. So that means I'm going to linearize over 1 revolution, and it's going to spit out 36 linearization files. And then we're going to open like the Python script is going to read all of those lean files, run them through the MBC transformation, and then you get an average A matrix because each of these lean files have an A matrix. You average them through this MBC transform, and then you get the natural frequencies. Yeah, I think there are details, of course. How does it look? I hope I gave you the results. Not really. I gave you only 1 lean file, but if you run it, you should see 36 lean file in there. It's going to take time. It's running. You don't know when it's going to linearize. We're going to look at the output file. Another thing with PyDatView is you can open and just click reload when you're impatient. You just do reload, 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 reload until something happens. And you can look here. It's still running. I think it linearized. What we want to look for is the rotor speed. You can see it's varying because I'm doing the generator degrees of freedom is on, right? So the control, we need the controller to the generator torque to tell us. And in the terminal, you can see now OpenFAST has found a steady state. And if I reload in PyDatView, I can see that what it means is, yeah, rotor speed has reached some kind of equilibrium. OpenFAST has detected this and is running the linearization for 1 full revolution. Blade pitch is 0. It'd be nice if it gives you the azimuth. We should add this actually so that you could see those different azimuths where it's linearizing. And if you look in this folder, you have the bunch of lean files being created. And what is that? Yeah, you can look at those Python script to then post-process and run the MBC3. I think I wanted to show you this thing. Basically, if you don't use trim, if you say CalcSteady equals false, you can still, the system is still going to reach an equilibrium, but it's not going to be the 9 meters per second that you wanted. So this is where CalcSteady, this new option, is pretty useful. Anyway, this is the process for linearization. Next is the Campbell diagram. Is there a question at the moment? Not too much. So this is fine. What we did here, what did we do? We linearized for 1 rotor speed and 1 wind speed. And if you run the Python script, it's going to give you the frequencies and damping for this particular wind speed and rotor speed. The Python script probably gives you a plot like this. So at 8 meters per second, you have different modes in your structure based on which degrees of freedom we've activated. And you could try to identify those modes. And you have some flap and edge modes, and you're going to have some tower modes. If I turn the tower on, the tower is not on, so there's no tower modes. And you can look at the damping. Is it negative? No. So this system is stable, even with the aerodynamics on, no problem. The idea is you repeat this for multiple wind speed and rotor speed, just to look at how your turbine is for the entire range of operating conditions. And so that means we have Python scripts to generate this, all those input files for you. Examples are provided here. And in that case, I have probably 1, 2, 3, 4, maybe only input files just to make it run fast. And then you plot those frequencies and damping as function of wind speed. And this is how it would typically look like. And in that case, now I have the tower again. I have the tower that shows up here. So this is my first tower mode, fore, aft, and side. That's the frequency on that side as function of wind speed. This is the damping. And you can see how things evolve as function of wind speed and rotor speed. What you would typically expect is your blade modes are going to separate as the rotational speed increase, and which is what happened here. I'm a bit suspicious about my x-axis here. My guess is the x-axis is wrong, okay? Probably because of a version issue. But usually you see the split until you reach rated speed, and then after rated speed, your rotor speed is constant, so you don't see the split anymore, so your modes are constant. I'm guessing this is what happens here. We have two different rotational speeds, so the mode splits up, and then we have constant, more or less constant frequencies. It's not going to be, for modern blades, things go a bit all over the place. What can I say? Any questions maybe here? There's like a bunch of guidelines. Like I said, it's not easy to run all of this. Identifying which mode is which can be very difficult. It takes expertise, and right now the way we do it is we have a CSV file that you can open in Excel, and you do it manually. You kind of move those curves manually. So it's a tedious process. We are improving on this. So once again, if you wait a couple of years, it's gonna get better. Less than a couple of years. Okay, let's be fair. We have at least something that works great. I think I have it in my package. I think I have your program. The program that Derek did is really good. I'm highly optimistic. Damn it, where did I put it? I can download it. Oh shoot, I'm sorry. Well, that's about it. But it's a GUI that can help you visualize those modes and hopefully identify the modes a tiny bit better and generate this thing. And the vision we have is in the future, you can look at one given point, you double click on it, and you see the 3D structure moving according to that mode. And then you can more easily identify those modes. I think that's about it. There's a lot in the slides. If you're curious, I would recommend reading the slides and trying the examples, trying the Python scripts to get a bit more familiar with it. But that's about it, yeah. All right, 3:30. We've covered all the materials I had, so now we can have a little break. Any questions so far? You're completely burnt out, huh? Got one question. Yeah.
Like if I specify question to run for 100 seconds, but use the calc steady option, it terminates it at it finds steady state.
It doesn't run any further. That was this case I ran as well. It was probably for 500 seconds or 400, and you're right. It stopped at 120 seconds.
And where does it linearize?
It linearized here in the last revolution, and you can see it maybe, or I can plot the azimuth, and you can see what OpenFAST gave me in the terminal. It tells you the time. It linearized between 119 and 126. So you can see between 119 and 126, that's about this revolution from here to here.
So if I want to linearize at let's say at the end time of my simulation, so for some particular speed.
Yeah, I often do this. Yeah. Then you don't use calc steady.
Oh.
You don't use calc steady. That's what we used to do before this calc steady option. And you set up, you would set the lean times here.
Yeah.
In that case, you would say, well, I want it at 600 second plus nothing works, numlock, 600 second, and then 600 second and 5.5, 601, 601.5 based on your RPM, right? You write 36 values here, and then it will do it. Or you just do it for one. More and more what we're doing when we're linearizing at the moment, we're trying to make the signal non-periodic. So we remove gravity, we remove tilt, just to avoid, I mentioned this averaging of the matrices, and we find that this is very sensitive to numerics. So we actually try to make the signals as periodic as possible. So we have wake mode equals 0. No, sorry, skew mode equals 0 as well, which is an option that makes sure that your wind speed is actually always perpendicular to your rotor. This way it's periodic. But yeah, you remove shear, you remove gravity, you remove tilt. Usually that's a good way to go. And tower influence. Then you only need to linearize at one time step. Just makes it easier.
And that list of things that you mentioned HCM model can be linearized, but the other one.
Some models can be linearized, not all of them. Is that what I said, or because that's true? Yeah, sorry. What did you say? Yeah.
No, I think Jason mentioned that.
Okay, yeah. So OpenFAST is going to complain if you start to use an option like you use turbulent wind. OpenFAST will tell you no, you can't do that. You use wave kinematics. OpenFAST is going, no, we want a fixed steady still water. For aerodynamics, there are also some options you cannot use. Very important for the aerodynamics, use wake mode, no, frozen wake equals true, or, well, I hope it's in the slide. I think it's in the slide. This, yeah, in aerodynamics, there's some things you need to be careful about. But yeah, OpenFAST will tell you at least what to do if you do something wrong. But if you don't use debamped, so if you use wake mode equal 1, use frozen wake equals true. I don't know, I should write this somewhere. Aerodyne, if wake mode equal 1, use frozen wake equals true. Otherwise, use wake mode equals 2, and OpenFAST is going to tell you what to do. Yeah.
I think we should break because people are tired. Thank you, Emmanuel.
Yeah, nice. Congrats to you.
Back forward. Thanks.
It's not happy. Yeah, I think my computer is just having a hot time. Just give me a second and I'm good. There you go. Should be good.
So if I were to follow it, just a few message. So there is the way around. Then use essentially the Python script, right? Rating optimize step. Change run that again. You have examples of that. Let's say the twist on. I know. So, but that's what I would first use the other. Yeah, just no. I struggled in the past. So I used to make test and then just okay. So I can get the aerodyne right, and then it's just like yeah. So you yeah, there's different ways. Okay.
It's gonna, it's probably fine.
Yeah, and one, really, I would say, well, it's an Fiji. Yeah. You kind of have yeah. Yeah. Okay. If you do it that, guys have Python recording in the class library. At the end of the day, it's almost. Oh, right. Yeah. And you need to make sure you compile the OpenFAST library Okay. Then you mount. I see. Yeah, yeah. Yeah, but either way, I mean, that's. Yeah. But then you say you can pass. Yeah, because it's also. It has all the. Thing that. We don't forget distribute running OpenFAST on multiple cores, right, during
Yeah.
optimization. So they have this built in on. Okay. Okay. So learn why. Okay. I mean, like seeing things how they work. So that's why I would like to do it. For us, kind of simple, like Exactly. So that's what I like. That's why you have PyFast.
Okay.
PyFast is here to do this kind of.
Okay.
Because then you have input files. Otherwise, input files are rewritten.
Yeah, it's all.
So that's why I would recommend using PyFast and then understand the workflow.
Yeah. Okay. Thank you. Nice.
Really? Yeah.
I have to go to the raw meeting.
Yeah, yeah. Sounds good. Great. Thanks for being here.
Yeah. How's it going? Pretty good. No. And I was like, I've only seen you through a computer screen. So yeah, I was like, wait a second. I was pretty sure that's Andy, but then I was like, now that the way he's looking at me, I'm not so sure. No, I was back in my. Okay. Yeah. Okay. Yeah. Basically, it's actually it's free. And honestly, I was hiding in the crowd. So yeah, love to clear. Yeah. I mean, I was here for the conference and here for tomorrow, so might as well. Well, awesome. Yeah. What are you working on? I'm still doing pretty much the exact same thing that I was doing before. Okay. Got my aerostructural plates all going with gradients through it. That was, and I recently got it, so I had discrete and steady adjoint around the solvers and then algorithmic differentiation for everything. Everything validated. And now we're deciding to take a slightly different course, so I'm gonna have to like resurrect some old code, but it shouldn't be too bad. So should be finishing that up here. I want to say that I should read
myself, but